Hello everyone. This video will be on the 3.5 section of the IBAA curriculum. Please pause the video for a second to look at the concepts, contents, and formulae for this section. One sentence that summarizes this section is, a unit circle can help us remember exact values of trig ratios of 0, pi over 6, pi over 4, pi over 3, and pi over 2. Let's first start by drawing a unit circle. A unit circle is a circle with a radius of 1. Simple enough, right? Then let's identify one angle, theta, where the line theta angle away from the positive x-axis. Then we can identify the coordinate of the point at the end of the line. We know that we can construct a triangle from the origin to the point. We can use the trig ratios to find the adjacent and opposite. So knowing that the hypotenuse is 1, okay, we can find the adjacent part, where so cosine theta would be adjacent over 1. I know that A is cos theta. And similarly, we can find that the opposite is sine theta. Because we're interested in the coordinate values of the point, we know that x coordinate will be the same as A, so cos theta, and the y value will be the sine theta. Now, that is our main character for our angle, because we're in the first quadrant. What if we go to the second quadrant, the third, the fourth? Let's go to the second quadrant and then also construct an angle. So perhaps the angle over here would be something like that. If that angle is something like, x, then I know that the angle of this has to be pi minus x. So if I make the triangle over there, stay there. Okay, whatever. In this case, I can do the same thing. I'm interested in the coordinate plane of that. I know the hypotenuse is still 1, and the adjacent has to be the cosine. So the adjacent will be the cosine pi minus x. And then the opposite will be sine pi minus x. Okay. However, because we're in the left-hand side, we're in the second quadrant, our x value has to be negative. So we're going to put negative cos pi minus x. Now let's quickly talk about the tangent identity. The tangent identity is simple, but you want to make sure that you understand the logic behind it. In this unit circle, we see that the adjacent is cos theta and the opposite is sine theta. In this logic, if we use the tan theta as opposite over adjacent, then we can conclude that the tan theta is sine theta over cos theta. Does it make sense? Now, let's look at some special angles that are worth noting and perhaps memorizing. Let's start with 0. If the angle is 0 radian, then what would the adjacent and opposite be? The angle is 0. The adjacent would be, will be 1, and opposite would be 0. Connecting this idea to our expression of the coordinate point on the unit circle, we can conclude that cos 0 is equal to 1. And also the sine 0 is equal to 0. Does this logic connect to you? Let's try the next one. What if the angle is pi over 6? Well, we can do the same thing. And let's construct the triangle over here. Another drawer, but let's try to make a triangle like that. And say that this is pi over 6 and it's a right triangle. Well, if the angle is pi over 6, then we know that this is a special triangle where the angles are pi over 6, pi over 3, pi over 3, and this is pi over 2, 90 degrees. This is the same as a 30, 60, 90 triangle. The length are always in the ratio of 1, square root of 3, and 2, right? However, since our circle's radius is 1 right now, we need to divide everything by 1. So we're going to change that into 1. We're going to change that into 1 over 2. We're going to change that into square root of 3 over 2. Okay? And therefore, we can find the cosine of pi over 6, which will be the adjacent, square root of 3 over 2. The sine will be the opposite, 1 over 2. You may pause the video for a second right now to try some extra ones on your own. Something like pi over 4, pi over 3, and pi over 2. Now, what if the angles get bigger than pi over 2? Let's suppose that we have an angle 5 pi over 6. It is a reflex. It is a reflex angle, so we have to make the triangle in this. So it's an obtuse angle, so I have to make the triangle in the second quadrant. So our triangle would look something like that. And we don't want that kind of triangle, so we're just going to make a triangle like this. And we know that this is going to be pi over 6 as well. Okay. And now, in this triangle, the opposite will be 1 over 2, and the adjacent will be square root of 3 over 2. However, this is in the second quadrant. We have to remember that the value has to be negative. Okay. So in the end, we get cos 5 pi 6 will be negative square root of 3 over 2. Sine 5 pi over 6 will be 1 over 2. Notice that I do not memorize all the multiples of special angles. But if you can remember the unit circle construction, you can always make them yourself on the spot. Lastly, let's take a look at the examples I've shown you earlier. We see that sine pi over 6 is 1 over 2, and sine 5 pi over 6 is 1 over 2. They're both 1 over 2. And if you're solving a triangle using a sine rule, and let's say that you're solving for an unknown angle A, perhaps, you're looking for A, and you're given that small a is 2, b is pi over 4, and small b is 4 square root of 2. And as you solve for sine A, let's try that. It's going to be a over sine A equals b over sine b. You know that a is 2 over sine A, I don't know that. B is 4 root 2, and sine of pi over 4. And if you have tried to make the exact values of the multiples of pi over 4, I know that sine pi over 4 will be square root 2. I can say that 2 sine A is 4 root 2 over root 2. Then when we solve for sine A, we know that we get 1 over 2. In this case, can you be sure what angle will your triangle be? Will it be pi over 6? Or will it be 5 pi over 6? You can't be sure. This is called an ambiguous case of a sine rule. Quite similar to our quadratic formula when we had two possible answers for the given set of values. Okay, so a trig equation question will have multiple answers. Okay? I hope you enjoyed this video and try some questions in this section to really master the skills that we have learned. Anyways, I'll see you in the next video. Best wishes.